In this video, we're going to talk about what a combustion train is and how it can be used to determine the empirical formula of a hydrocarbon. So we can use it to determine the ratio of carbon to hydrogen in a given compound, and if we know the ratio of carbon to hydrogen, then we'll be able to figure out what the empirical formula of the hydrocarbon is. So first, let's look generally at what combustion is. So we have some hydrocarbon, so that's a CH compound, and it has some number of carbon atoms and some number of hydrogen atoms. Then, with oxygen, gas, it is burned and produces CO2 gas and water. So in order for combustion of a hydrocarbon to happen, we need oxygen gas, and then the two products of combustion are carbon dioxide and water. So our combustion train has multiple different parts, and it works in a continuous flow format. So in from the left side, let's say, we have oxygen gas, because we need oxygen gas for combustion to happen. So we have oxygen flowing through this tube. Then we reach the first chamber, and in the first chamber, we place our sample. I'll call it S. And around that initial sample chamber, we have some heaters. And those heaters heat up the sample in the presence of oxygen and initiate the combustion reaction. And so that's connected to another chamber, which is a separate piece from the sample chamber, and these are made of glass. And in this chamber, we have some sort of drying agent. And this drying agent is a desiccant, and there's lots of different choices, but this desiccant absorbs the water produced by the combustion. In this case, we'll say the desiccant is magnesium perchlorate, but there's lots of different possible desiccant choices. And this absorbs the water. The oxygen continues to flow, and it pushes the remaining carbon dioxide into the next chamber, and in this chamber we have something that absorbs the carbon dioxide produced from the combustion. And so that's going to be a combination of some strong base, let's say NaOH, and calcium chloride. So our different parts, we have oxygen gas flowing in from the left side into our sample chamber surrounded by heaters, which flows into our chamber with a drying agent to absorb the water, and the next chamber that absorbs the carbon dioxide produced from the combustion. So our process, we have our unknown hydrocarbon, and we must weigh it initially. So we have our first weight, which is the hydrocarbon. Then we get our weight number 2, which is the initial weight of the chamber with the desiccant that absorbs the water. And our third weight is the weight of the chamber that absorbs the CO2. And we weigh these before the reaction happens. So the sample is placed in the chamber, where it is burned with oxygen flowing through the glass tube. So the sample is combusted, and it produces water and CO2 gas. And these products are flowing through the tube, and they enter the chamber with desiccant. And so the carbon dioxide and water flow into this chamber, and the water from the reaction is absorbed into the desiccant. So then the carbon dioxide continues to flow, and it flows into this third chamber with the base and calcium chloride. And the CO2 produced from the combustion reaction is absorbed in this chamber. And then the only thing that flows out of this third chamber is oxygen keeps flowing. So these two chambers are then weighed after the reaction is completed. And we subtract the original weights of these two chambers from the final weights to get the weights of the water produced from the combustion reaction and the carbon dioxide produced from the combustion reaction. And using those weights, we can determine the empirical formula. And and we're going to do a little example of that right now. So let's say we run a combustion train and we produce 6.76 grams of CO2 and 1.384 grams of water. So what's the empirical formula of the original hydrocarbon? Well, what we need to do is figure out how many moles of carbon are in the original hydrocarbon, and how many moles of hydrogen are in the original hydrocarbon. So our moles of carbon from our hydrocarbon is equal to the number of moles of CO2 produced in our reaction, because there's 1 mole of carbon in every 1 mole of CO2. And so that's equal to 6.76 grams of CO2. And we convert that to moles using the molar mass of CO2, which is 44.01 grams per mole. So grams cancel out, and what we find if we plug this into our calculator is that we get 0.154 moles of CO2. Now water's a little bit trickier, and we want to know the number of moles of hydrogen in our hydrocarbon, but that's not equal to exactly the number of moles of water produced, because every mole of water produced contains 2 hydrogen atoms. So for every 1 mole of hydrogen in our initial compound, half a mole of water is produced. In other words, we need to multiply the number of moles of water by 2 in order to accurately calculate the number of moles of hydrogen in the hydrocarbon, because for every mole of hydrogen in the initial hydrocarbon, half as many moles of water can be produced, because each water molecule contains 2 hydrogen atoms. So we do the same conversion, but we multiply the entire thing by 2 in order to account for that. So we have 1.384 grams of water, and we use the molar mass. So every 1 mole of water is 18.01 grams. Grams cancels, and what we find is that we get 0.154 moles of water of hydrogen. And now let's compare that to the number of moles of carbon, or CO2, since they're equivalent. Look, they're equivalent. So we have a 1-to-1 ratio of carbon to hydrogen based on the weights we got from the combustion reaction. So that means the empirical formula is simply CH. Now the molecular formula could be C2H2, C3H3, but that was just a little example of how to obtain the empirical formula of a hydrocarbon using the data obtained from a combustion train.